The discussion this week has focused on instrumentation and control, including SCADA. We introduced the concept of the electrical transmission of values recorded by instruments in a SCADA system or through a telemetry system by a 4 to 20 milliamp signal. The math this week is going to focus on how that 4 to 20 milliamp signal works, how mathematically it is equivalent, or the live signal, as we'll call it, is equivalent to the representation of whatever data is being measured. So as is true in most cases, we'll start with our formula sheet. The bottom right-hand corner of our formula sheet is where our SCADA formula resides. It refers to the 4 milliamp to 20 milliamp signal. And the formula that we will start with says live signal in milliamps minus the 4 milliamp offset times the process unit and range divided by 16 milliamp span. What is quite noticeably missing is an equal sign. What does this formula do? What does it give us? What are we calculating? So we're going to take the formula, we're going to tweak it a little bit to show what it does. And part of the reason why there is no equal sign in the formula itself is it changes a bit what the formula produces depending on the scenario that's given. And we'll talk about how that works. So to begin with, we'll take the formula as it's given to us on our formula sheet. So what you see now is exactly word for word what's on the formula sheet. But we're going to modify it a little bit for our uses. So the term live signal, we're going to just turn that into a variable, LS. LS stands for live signal. I don't want to write out live signal every single time I write this formula. So live signal, or LS, minus 4 milliamps. So 4 milliamp offset. We're just going to say 4 milliamps. It never changes. Because it's a 4 to 20 milliamp signal, because we don't start at 0, we start at 4, we have to use that offset because we are offset from 0, from the origin. Divided by 16 milliamps. 16 milliamp span. Again, the 16 never changes, so we're just going to use the 16. We're not going to write the word span every time. Just keep in mind where it comes from. The span from 4 milliamps at the bottom to 20 milliamps at the top is 16. 20 minus 4 equals 16. So it's 16 every time. So this part of the equation, LS, or live signal, minus 4 divided by 16, doesn't change. The 4 and the 16 are constants. Process unit and range, we're going to abbreviate with the variable R for range. The range of values that the instrument can measure. So for example, if you have a pressure gauge that is calibrated from 0 to 150 psi, your range is 150 because it can go from 0 to 150. If you have a flow meter that's calibrated from 1,000 gallons per minute to 5,000 gallons per minute, your range would be 4,000 because you start at 1,000, you go to 5,000. What's the difference between your maximum value and your minimum value? That's our range. What's really going to kind of tweak things a little bit is whether or not our minimum value is a 0. It really kind of simplifies things when it's a 0. And we'll do some examples in the next section with that minimum is 0 and sometimes when it's not. So what does the formula produce? Again, there was no equal sign. It's going to produce whatever we're measuring. Maybe it's a flow rate. It could be a variety of things. So keep in mind, and we talked about this before, that 4 to 20 milliamp span, that it's going to move proportionately with whatever's being measured. So if you recall from the lecture material, this little chart that shows you that when you're at 4 milliamps, you're at 0%. So again, using that example of a pressure gauge that's calibrated from 0 to 100 psi. If your signal is at 4 milliamps, you're at 0 psi. You're 0% of what it can measure. If you're all the way at the top of that range at 100 psi, you'd be at 20 milliamps or 100%. So the point being that as you move through your span of live signals from 4 to 20, whatever percentage of that total span that you've moved, the value that you're measuring is moved the equivalent percentage through its range. So for example, using that 0 to 100 psi example again, if you're at 12 milliamps, which is halfway through your span, From 4 to 12 is 8. From 12 to 20 is 8. So you're halfway through your span, meaning you're 50% of the way through your span. Means the measured value would be 50% through the range. So if you're calibrated from 0 to 100 psi, 12 milliamps is equivalent to 50 psi. Halfway through the span, halfway through the range. That's conceptually what the formula does. We'll look at it in a little more detail, and we're not going to actually use it in terms of percent. It's just a kind of a way to visualize it. The formula will stand on its own. So you can measure a flow rate. You can measure a level. You can measure temperature. You can measure chlorine residuals. You can measure pressure. All of these, the same formula applies. The units may be a little bit different. The live signals are all in milliamps. Your range will be in whatever units you're measuring, PSI for pressure, maybe gallons per minute for flow, whatever it might be. So the problem is going to set up what you're measuring, and then you're going to use the formula. The formula doesn't change regardless of what actual type of measurement it might be. So we're going to set these up when we do these problems with kind of a table. We'll start on the left-hand column with a live signal. Our live signal starts at 4. That's the minimum. Its maximum is always 20. And someplace in between is an actual live signal that corresponds to the data that we've measured. Using pressure as an example, we have a minimum pressure, whatever the bottom of our range is, whatever the instrument is calibrated for, and we have a maximum. So the problem is going to tell you, all right, it can go from 0 to 100 psi is the example we've been playing with. And then whatever the actual measured value is someplace in between that minimum and maximum. And as we said before, as the live signal moves through its span, the pressure moves through its range by the same proportional amount. If you're 25% through your span, you're 25% through the range. And so that's what conceptually it does. Now let's take a closer look at the formula itself. To begin with, we're going to need a range in every problem. The range is the difference between the maximum value and the minimum value that can be measured. So again, as we said before, if it tells you it's 0 to 100 psi, the maximum is 100, the minimum is 0, 100 minus 0 is 100. There's your range. If it tells you your meter is calibrated from 1,000 gallons per minute to 5,000 gallons per minute, your maximum is 5,000, your minimum is 1,000. 5,000 minus 1,000 would give you a range of 4,000. So again, things are a little bit different if that minimum is not 0. Our span is just like the range is the maximum minus the minimum. Our span is the maximum live signal minus the minimum live signal, but those numbers don't change. So it's always 16 milliamps. So taking a closer look at this table and what we're actually calculating. If we look at the difference between the actual live signal and the bottom of our span, and we divide it by the total possible span, we're going to get a percentage that it moved through. That's what that little chart table we've been looking at would say. If you get to 12 milliamps, 12 minus 4 is 8, 20 minus 4 is 16, you're at 50%. So the whole point is, and the reason this works, is that percentage is going to be equivalent to what happens on our actual values, on our pressure column in this case. So the measured pressure minus the minimum, just like we had LS minus 4, we have the measured pressure minus the minimum, divided by that total possible range of values, the maximum minus the minimum, is the same percentage. That's why whatever percentage the span has moved, our measured value, in this case pressure, has moved the same percentage through its available values. So those two kind of equations on the left and the right are equivalent. They both are the same percentage. Since they're both the same percentage, since they're equivalent, we know that the span is always 16. We know that Pmax, let me back up so we see what just happened there. On the bottom of our right-hand side of the denominator where we have Pmax minus Pmin, the top minus the bottom, as we've said, that is equivalent to range. So let's substitute our range variable in the equation. So now we have LS minus 4 divided by 16 is a percentage. Our P measured minus our minimum pressure divided by our range is equal to the same percentage. Well, since they both equal to the same percentage, let's take that percentage symbol out of there. Now the left-hand side and the right-hand side are the same thing. in order to make this turn back into the formula that we started with, let's multiply both sides times range. And what's going to happen on the right-hand side is our ranges are going to cancel out. And when they cancel out and disappear, now we have LS minus 4 divided by 16 times range is equal to our pressure, which is the exact formula we started with. The thing to keep in mind is what it really is equal to. And this is the reason why it's challenging to put on our formula sheet, because the variables can change, but it also is different depending on what the value is at the bottom end of our range. If it's 0, then it's very simple, because when you subtract 0, it just goes away. So the simplest form of this equation are LS minus 4 divided by 16 times range is equal to the pressure that we measured, the exact pressure that the instrument is reading. It changes if that number is not 0. So when we do the example problems, we'll talk about the fact that in all cases our range is Pmax minus Pmin. In all cases, what we actually equal to is the measured pressure divided by the minimum pressure. It's just that things get a little simple when that minimum pressure is 0. But if we keep in our minds that we always have to subtract the bottom, then we get in less trouble when there actually is a value as opposed to 0 for that minimum pressure. So we'll go from here into applying this to a variety of different example problems. They will include those that have 0 for the bottom end of our range, as well as those that have a value. We'll do some where we will calculate the measured value. We'll do some where we're given the measured value and have to calculate the corresponding live signal. So we'll do kind of every manipulation of the formula we can, and hopefully it all makes sense.